Okay, so show that the temperature here is 386 kelvins, right? Here's going to be our strategy, okay? We know that CA is adiabatic, right? We know the pressure at A is 4E6, right? We know the volume at A is 1.5 E minus 4 cubic meters, right? That's pascals. Okay, we know that this is an adiabatic process, so therefore we can find, and well, we also know that the volume at C is, it's twice the volume at A, even though the graph doesn't make it look like that. Okay, the volume at C is twice the volume at A, so we know the volume at C is 3 E minus 4, right? Because it's twice 1.5 E minus 4, correct? So our strategy is going to be this. We're going to use this equation, because this is an adiabatic process, right? It has to equal pressure C, volume C to the 5/3, okay? We're going to use that to find the pressure at C. Then we're going to use the ideal gas law, right? PV is nRT. So the pressure, the temperature at C is going to be the pressure at C, the volume at C divided by NR. Okay. Oh, we don't know the moles, do we? Okay, so we're going to have to find the moles as well, I feel like. Okay. So so that'll be another strategy, right? So, but we can figure out the moles because we know this, right? So the moles will be something, right? Okay, so 3-step process here. It's 2 marks, 3 steps. Unless there's an easier way to do it, I don't know. This is the way I did it. Okay. Oh, I know. You can use the combined gas law to find the temperature at C without finding the number of moles. We kind of need the number of moles, I feel like. Okay, so let's we can do it 2 different ways. So step 1, let's do this. I feel like that's a good step 1. Okay, so 4E6 times 1.5 e to the minus 4 to the 5/3 equals PC times 3e to the minus 4 to the 5/3. Okay, this is like higher mathematics coming up. All right, so 4e6 times 1.5 e minus 4 raised to the 5 divided by 3, right arrow divided by 3e minus 4 raised to the 5/3. Whoops, I just raised it to the 53rd. Okay, are we ready for this? Okay, I'm getting that the pressure at C is 1.259921, and that's E6, right? And it's not putting it in scientific notation for me, but that's what it's got to be, right? So I'm going to store that in C. Okay. Let's find the number of moles just for kicks and giggles, okay? The number of moles is going to be PA VA over RTA, right? And they tell you the temperature is 612, right? So it's going to be 4E6, that's a 4. 1.5 E minus 4. R is still 8.31. And it's 612. Okay. So 4E6 times 1.5 E minus 4 divided by 8.31 divided by 612. And it's not very much. Okay, so the moles are 0.117977 moles. Okay, so let's store that in alpha n for moles. Okay, so now I've got the value for C, I've got value for the moles. Okay, so now we can find the temperature at C. Okay, the temperature at C is going to be the pressure at C, which is 1.2, it's this guy here that we figured out, right? 1.259921 E6 times the volume at C is 3E minus 4. And it's 3E minus 4 because remember it's twice the volume at A, and the volume at A is 1.5, right? And then divided by N, which is 0.117977, which we just figured out here, right, times 8.31. Okay, so here we go. So I'm going to go alpha C. There it is. Okay, so that guy times 3E minus 4 divided by the number of moles divided by 8.31 is 385.53, okay? Okay, so that is about 386 kelvins, right? So that's the one way to do it, right? The other way to do it would be if we didn't want to find the number of moles, we could just go PA VA over TA is equal to PC VC over TC, right? So we can say 4E6 times 1.5 E minus 4 over 612 equals, the pressure here is 1.29259921 E6 times, and this is 3E minus 4 divided by TC, right? Let's try that. That should work. 4E6 times 1.5 E minus 4 divided by 612 gives you that. And then I'm going to go this guy times 3E minus 4. And then I'm going to divide by that number I just got. Let's see. And again, when I do this, of course, I get exactly the same answer, right? So TC is 385.53 kelvins, which is about 386. Okay? So anyway, there you go. That's the thing.